In this video, we're going to think about the maximum likelihood estimator, or MLE, for a univariate, so it's a one-dimensional Gaussian distribution, or a normal distribution, as it's sometimes called. And I don't remember exactly how this goes, but we're going to figure it out. So in general, the MLE for a parameter, theta, the maximum likelihood estimator, is the value of theta that maximizes the probability of the data. Maximizes this likelihood function. Probability of the data given that value of theta. And so what is theta going to be for us in this case? Well, let's write down what the univariate Gaussian looks like. So here we'll define so we're assuming that the distribution for a single x, and x drawn according to a univariate Gaussian. So we'll say x is distributed normally with some mean. Let's take theta to be the mean. Sometimes you use mu, but let's take it to be theta, since to be consistent here. And so then the PDF for x is what we're writing, and that is 1 over the square root of 2 pi sigma squared times e to the, or we can write exp of, it's the exponential function of, minus 1 over 2 times sigma squared times x minus theta squared. That is the density for a univariate Gaussian. And now, okay, so let's see here. So if we want to, oh, okay, so now for the typical setup, we're given some data, right? We're given x1 through xn before I start to jump the gun and maximize this thing. And each of these xi's is drawn according to this same distribution, this normal. Theta, sigma squared, and their IID. So what's the distribution for the data given theta? Let's write that. So the probability of d given a particular value of theta is the product, so we're assuming that these are independent. So this is also, if we just rewrite what this is, we don't take the product yet, this is the probability of getting this sequence of points. Maybe I should say it's the probability. Let me make these actually. We're thinking about them as random variables, but this is I'm writing lowercase for the values that these are taking. So I should to be more precise here, let me say that these are particular values, and we're thinking of them as values where so xi equals little xi here. And this conditional density on the whole product, by assumption, they're IID, so this is the product of the probabilities. And then we can apply this formula, since they all have the same density, and this becomes, so let's write out what that is. So we got this first part to the n, exp exponential, and then we've got, so the product of exponentials becomes the exponential of the sums. So this is minus 2 sigma squared. We can pull this constant factor out, and we get this sum over xi's as I goes from 1 to n. So that's what this product equals, just plugging in this formula. And now we want to maximize this. All right, to get the MLE, we want to maximize the probability of the data given theta. So we want to maximize this thing, and theta here, for a normal, theta ranges over the whole real numbers. So the space of values theta that we're maximizing over is all the reals. And so we'll do the calculus thing. Looks like, the calculus thing is just the thing to do here. We're just going to differentiate and set the derivative equal to 0. But before we do that, let's note, so, oftentimes, especially when you have a distribution that's e to the something, and the thing you're trying to maximize is in the exponent, then it makes your life much easier to take the log. And a lot of distributions called exponential families have this sort of property. So oftentimes we will want to take the log. So let's take the log first. Oh, and I should mention why can we take the log? Well, this is equal to, because the log, log of x, put log of x here, and this is x. That is, it just looks like this. It's a monotone increasing function. So it's order preserving. So if we maximize this, that's the same as maximizing the log of it. So this equals, I need a little more room. This equals argmax over theta of the log of the probability of d given theta. So we can take the log here and maximize that instead. So let's do that. Take the log, so we get n times log. Let's go ahead and do it. This is 1 over, so this is n. This is 1 over 2 pi sigma squared to the or this is 2 pi sigma squared to the minus n over 2. So let's go ahead and do that. We can pull down the exponent when we take the log. So we get 2 pi sigma squared. Log kills the exponential, and we get minus 2 sigma squared times this sum. Okay. So we've got that. And now we're maximizing with respect to theta. So let's differentiate this thing and set the derivative equal to 0. So this is the usual calculus thing. So we differentiate with respect to theta. And this, by the way, this thing is sometimes called the log likelihood. This is the log likelihood because this is the likelihood function of theta. And this is the log likelihood. So we differentiate the log likelihood. This part is a constant with respect to theta, so it's just 0. And what do we get over here? So let's see. So if we differentiate, so of course the derivative moves through the sum, linearity of differentiating. We pull down a 2, and then we get, so we'll just include the minus there for a second. So we get 1 over 2 sigma squared, sum, differentiate this, we get 2 xi minus theta, or not squared, we have differentiated, times minus 1, right? We take the derivative of xi minus theta, and that's minus 1. And the minus 1 kills this minus, so we just get plus here. And now let's go ahead and move the sum through here, and we get 1 over 2 sigma squared. Well, let's go ahead and cancel the 2. That'll simplify things a bit. 1 over sigma squared, sum over xi minus, and now, let me make, okay, we'll do it this way. So we get so we get the sum over the xi's minus the sum of the thetas, and this is the sum from 1 to n, so that's just n theta. And so we distribute this through, we just get, oh, actually, well, we can cancel this, right? Because we just have a 0 here, we can multiply both sides by sigma squared. So this just cancels, just goes away. in our maximization. And so if we move the n theta, now we've just got it. Right, we move the n theta over to the other side and solve for theta. So this implies theta equals 1 over n times the sum from 1 to n of the xi's. So we know that this is a critical point of this function. You know, when the derivative equals 0, it's a critical point. And to verify that it's a maximum, we wanted to maximize this. We want this to be a maximum, and so we need to take the second derivative. So let's think about if we took the second derivative of this. This is the first derivative. If we took the second derivative with respect to theta, we would end up with minus n over sigma squared. Or actually, it would be, I guess, yeah, because the 2's cancel. So the second derivative would be log whatever equals this thing. Right, yep, because that just goes away. So we get this, and this is negative. We're always assuming that sigma squared is some strictly positive value to make our distribution, you know, a well-defined thing. So this is fine. So we get minus n over this, and when n is, well, for any n, right? This is not finite. This is meant to say negative. As long as we get at least one data point that's negative. So that means, right, so that means that this is, in fact, a minimum. So this is a unique critical point, and the derivative is strictly negative, so it is a minimum. And we call this minimum, right? That was the definition of the MLE. So let's go ahead and label it what it is. This is theta MLE. It's the maximum likelihood estimate of theta because it's maximizing this log likelihood, which is the same as maximizing the likelihood, and that was what the MLE was. Right, we took the log likelihood, right? So we took the likelihood of the data, we wrote out what that was, we took the log, and we observed that maximizing that was the same as maximizing the original thing. We did the calculus thing, we differentiate, set it equal to 0, and then we find that it is in fact a maximum, unique maximum, and it is this thing. So this has a very natural interpretation. So here, at least in this case, theta MLE equals the sample mean. So it's equal to x bar. Sometimes we write this quantity as x bar, and it's called the sample mean. It's just the average. And this is, in some sense, the most natural estimate of the mean, right? Remember, theta was the mean of our normal distribution, right up here. Our assumption was that we had a normal distribution with mean theta. So when we get all of our observations to the maximum likelihood estimate for the mean says just take the average. And that's what this does. So this is a nice example of a very easy to compute a maximum likelihood estimate, and also one which has a very natural interpretation as the sample mean.